Hello and welcome to this GeoStudio Tech Talk on the compound strength material model available in Slope W. I'm Catherine Dompierre and I work with the GeoStudio engineering team here at Seequent. Today's webinar will be approximately 30 minutes long. Attendees can ask questions using the chat feature. I will respond to these questions via email as quickly as possible. A recording of the webinar will be available so participants can review the demonstration at a later time. GeoStudio is a software package developed for geotechnical engineers and earth scientists, comprised of several products. The range of products allows users to solve a wide array of problems that may be encountered in these fields, including stability analysis, the movement of water, contaminants, air, and energy through the ground, and stress and deformation in soil and rock. Today's webinar will focus specifically on Slope W. To introduce today's webinar topic, let's consider this slope. It is an idealized slope with simple features, allowing for more efficient numerical analysis. The nice thing about this idealized slope is that it requires the definition of only one material model. But in many cases, idealizations such as these may be too far from reality to truly capture a slope's resistance characteristics. For example, what if our slope featured many joint sets or weak layers? Should we then add new materials to each distinct discontinuity? How many material models would we need to define to perform the slope stability analysis? To streamline the modeling process, a simple and effective material model is required to simulate systems such as the one shown here, allowing for the definition of joint sets and weak layers so that the analyzed slip surfaces incorporate discontinuities in resistance. The compound strength material model provides this functionality in Slope W. GeoStudio 2022.1, our most recent release, includes many improvements to this material model. Today we will take a deep dive into the material model and see how it can simplify your workflow when dealing with rocks and soils where joint sets and weak layers exist. To properly understand how the compound strength material model works in Slope W, we need to make a brief detour into the world of geology. A rock mass such as this one includes many joint sets where the resistance will be lower than what is found within the intact rock mass. In the field, geologists will map these joint sets when characterizing the rock masses. For each joint set like this one, geologists will measure dip and dip direction, or alternatively the strike. The strike is the orientation of a joint set's horizontal projection with respect to the magnetic north. The dip direction is orthogonal to the strike and represents the direction toward which the joint set is heading. Finally, the dip angle is the angle the joint set makes with respect to a horizontal ground projection. By definition, the dip angle is a value from 0 degrees to 90 degrees. When defining the compound strength material model in Slope W, the dip direction and dip of a joint set or weak layer are required. As its name implies, this material model is in fact an aggregation of other materials stitched together into a single material. In this figure, the green compound strength material is being defined below. The yellow base material represents the intact rock or soil, which is the matrix unaffected by the joint sets or weak layers. Finally, the blue joint material exists within the base material over a certain range that needs to be specified. Both the yellow base material and the blue joint material exist as distinct materials in Slope W, where each is defined using the constitutive model of choice. As such, the base material could represent an intact rock mass, which might warrant the use of the Hook-Brown material model. The joint material typically represents a weaker stratum, which could be described via the Moore-Coulomb material model, for example. Exactly which material models are used for the base and joint materials does not impact the compound strength material model itself, as it will accept any base and joint material, regardless of their specific definitions. When defining the compound strength model, the dip direction of a joint set is required. In 2D, joint sets are assumed to be aligned with the cross-section, so dip direction values are more or less irrelevant. Since the cross-section is considered orthogonal to the north direction in a 2D GeoStudio analysis, Any dip direction value ranging from 0 degrees to 180 degrees is considered as 90 degrees. Conversely, dip directions ranging from 180 degrees to 360 degrees are considered as 270 degrees. The second input for the compound strength material model is the dip. As stated before, the dip is a value from 0 degrees to 90 degrees. In the image on the right, the dip is represented by the dark gray line in the middle of the section representing the joint material, which is blue in this case. By definition, a positive dip will always be plunging toward the bottom when the dip direction takes a value from 0 degrees to 180 degrees. Conversely, a positive dip would be aimed upward if the dip direction takes a value between 180 degrees and 360 degrees. The third set of inputs includes two ranges, range A and range B. Range A delineates the zone where the resistance is solely controlled by the joint material model. This is defined by an angular value extending from the dip. Range B specifies a transition zone where the material resistance is calculated by both the joint material and the intact base material. The exact shear resistance used is linearly interpolated between both materials depending on the specific angle of the slice base used in the slope stability calculations. For a clearer understanding of this material model in slope W, let's take a look at a simple but interesting example where the power of the compound strength model is clearly demonstrated. In GeoStudio, this example features a slope stability analysis of a rock cut for the construction of a road. I will therefore create a 2D slope W analysis and give it a relevant name. I will come back to the Define Project window later on, but first, let's create the geometry for our analysis. I will draw an intact rock mass that is 200 meters wide by 50 meters high. To better view my geometry, I will change the scale of the analysis right away to 1 to 600. I will then draw my rectangular geometry using the Draw Regions tool. The rock cut will be centered around the x is equal to 0 meter axis, so the domain remains symmetrical. I will use the Split Regions tool to quickly create the rock cut. And remove the region representing the rock mass that will be cut from the intact mass. If I were to perform a stability analysis on a rock mass using this symmetrical domain, I would normally obtain identical results, no matter which side of the rock cut I choose to analyze. But what if my rock mass actually features two joint sets? We should probably expect that the side of the rock cut, which is preferentially aligned with the most joint sets, should show a lower factor of safety. Let's verify this using the compound strength model. To define the material, I first need to define the intact rock mass material. And then the two joint sets the project geologist has identified during the field investigation. The intact rock material will be modeled using the Hook-Brown material model. I will assign a unit weight of 20 kilonewtons per cubic meter, a UCS intact value of 20,000 kPa, and the other parameters will be calculated from an intact rock parameter of 10, a geological strength index of 35, and a disturbance factor of 0.9. Finally, I will set the maximum confining stress for sigma 3 to 300 kPa. The two joint sets will be modeled using the Moore-Coulomb material model. Joint set 1 will have a unit weight of 20 kilonewtons per cubic meter, a cohesion of 5 kPa, and a friction angle of 26 degrees. The second joint set will have the same unit weight, but the cohesion is 0 kPa and the friction angle is 18.5 degrees. Once these three materials are defined, I can proceed with defining the compound strength material. This material will have a constant unit weight, which corresponds to the unit weight of the intact rock and joint sets. I will choose the intact material to represent the base material where the joints are absent. I will add the first joint set and define it following the project geologist's report. Its dip is 50.5 degrees, and it has a narrow band where only the joint resistance will be used. Thus, I will set range A to 1.5 degrees and range B to 7.5 degrees. Finally, I will select the set 1 material to be associated with this joint set. Next, I will add the second joint set, which features a dip of 3.75 degrees, so it is almost horizontal. For this joint, range A will be 2.5 degrees, and range B will be 8.75 degrees. Again, I must select the material associated with the joint set to be set 2, which we had previously defined using the Moore-Coulomb material model. With the two joint sets added, the compound strength material definition is complete. As you can see, it is very easy to add as many joint sets as necessary to a single compound material. I then will draw the compound strength material onto the entire rock mass. This single material represents by itself the rather complex anisotropic material surveyed in the field. To proceed with the slope stability analysis, I will first analyze the left side of the rock cut. In the Define Project window, I will rename the analysis accordingly. Make sure the direction of movement is correctly set from left to right, and then choose the block-specified slip surface option. When defining the left and right blocks for this slip surface definition type, we are providing the solver with grids to anchor the bifurcation points of a 3-segment slip surface. We also specify the range of angles the slip surface should enter or exit each block. This allows us to force our trowel slip surfaces to mobilize the resistance following particular orientations we wish to study, which in our case is the joint set's dip direction. Once the trowel blocks are specified, I will reopen the Define Project dialog and clone this analysis. The new analysis will be used to study the right side of the rock cut. I will ensure the slip surface direction is from right to left. Then I will define the trowel slip surfaces using the left and right blocks, just as I did for the left side. I'm now ready to solve both analyses by pressing Start in the Solve Manager dialog. To take a detailed look at our results, let me jump back into the presentation. To summarize our example, the rock cut domain consists of symmetrical slopes where a compound strength material model is used to represent joint sets measured in the field by the project geologist. The slope stability analysis results show a factor of safety of 1.47 on the left side and a factor of safety of 2.03 on the right side. How can we obtain different factors of safety for each side? Of course, the answer lies in our definition of the compound strength material model. To properly understand the specifics, let's take a closer look at the left side of our domain. In this figure, we see the specified blocks through which the slip surface must go. There are two white inflection points which mark changes in the angle at the base of the slices in green. These angles are negative by convention since they go up from the horizontal direction. Let's plot the base angle with respect to the x-coordinate, starting from the leftmost point in the domain. To calculate the mobilized shear resistance available at the base of each slice, these base angles must be compared to the compound strength model definition. This schematic view of our material includes the intact rock as well as the two joint sets. To help us view how each joint set relates to the slip surface base angle, let me identify the transitions between the intact material and the joint sets via the appropriate angles. The base angle of the first part of the slip surface is negative 48.5 degrees, which falls into the transition from the first joint set and the intact material. The base angle of the middle part of the slip surface is negative 38.8 degrees, which falls into the intact material. Finally, the last part of the slip surface has a base angle of negative 2.5 degrees, which falls directly into the second joint set material. When the solver calculates the available shear resistance at the base of each slice for the slip surface, an equivalent friction angle is calculated based on where the base angle falls with respect to the compound strength material definition. For the first section of the slip surface, the mobilized friction angle is a combination of the first joint set's resistance and the intact rock mass. For the middle portion of the slip surface, the mobilized friction angle only depends on the intact rock mass, which in this case uses the Hooke-Brown failure criteria. Finally, the friction angle for the last section of the slip surface only depends on the second joint set and is constant at 18.5 degrees per the Moore-Coulomb material model it uses. This low friction angle is used for the greater part of the second half of the slip surface and influences the resulting slope stability. This assemblage of mobilized friction angles, given the slice's base angle and the compound strength model definition, ultimately yields a factor of safety of 1.47. As we had already noted, this is quite a bit lower than the factor of safety for the right side of the rock cut, which is 2.03. By performing the same analysis as we just did for the left side, we can draw the following plot for the base angle of the slip surface and the mobilized friction angle. Plotting the base angle onto the compound strength model definition diagram reveals that the first section of the slip surface aligns with the transition from the second joint set to the intact material, while the second and third portions of the slip surface align with the intact rock mass. This assemblage of base angles and the corresponding friction angles yields a higher factor of safety than for the left side. The left side of the slope had lengthy sections of its slip surface which mobilized low friction angles in the low resistance joint sets. Conversely, the right side slip surface mostly mobilized the intact material and shows a higher general friction angle and thus a higher factor of safety. This simple example demonstrates why the compound strength material model is a useful and powerful tool to add to your Slope W arsenal. With minimal work, we were able to demonstrate how the material anisotropy, which is embedded into this material model, influences the limit equilibrium analysis results based on how a given slip surface mobilizes the jointed rock mass. But Reality is rarely this simple. Let us take a quick look at a more complex example where the compound strength model is used again. Back in GeoStudio, I have set up a slope W analysis with a rather complex geometry where the geology features many different materials. The project geologist identified many joint sets for these various materials and tested their resistance in the laboratory. The materials created in Slope W reflect these measurements via the creation of various compound strength materials. For instance, the DG1 and DG1 joint materials are respectively used as the base and joints for the various DG1 compound materials. Each compound material includes the same base and joint materials, but with varying joint dips based on the field measurements. The same approach is used for the two other sets of compound materials, labeled FWZ and MCS. You can see how easy it is to create various compound strength materials based on the same intact and joint materials, thanks to the simple user interface offered in Slope W. With the geological units mapped onto the domain, we are now ready to solve this slope stability analysis. But with such a complex geology, where would we even start? Inferring a first guess as to where the critical slip surface might be in a complex environment can be challenging, especially when compound strength models include more than the eye can see. Fortunately, Slope W now has a tool available to help guide us in these situations. By going into the Define Project window and navigating to the Slip Surface tab, there is a new slip surface option available, the Cuckoo search method. This nature-inspired search algorithm will work to filter through slip surface trials in the search for the most critical slip surface. You simply need to set the number of iterations allowed and the number of nests from which the cuckoo birds should begin their journey en route toward the optimal solution. No need to specify entry and exit points for the cuckoo birds. They will find their way. For this analysis, the cuckoo search method yielded a factor of safety of 1.12. The base angle varies along the slip surface, which intersects many compound strength materials. Along the way, the mobilized friction angle is calculated just as we have seen in the previous example, with contributions from the intact and joint materials. The mobilized cohesive strength is calculated similarly and is a result of the compound strength material models used to define the geometry. The cuckoo search method navigated this complicated geological environment to find the critical slip surface. Keep an eye out for a future webinar to focus specifically on this new feature where we will explain how this nature-inspired algorithm works. This concludes our webinar on the compound strength material model. As we have learned today, the compound strength model is the perfect tool to represent an intact soil or rock matrix comprising one or several joint sets or weak layers. It is very easy to define in Slope W thanks to a dedicated user interface. With the compound strength material model, you can now simulate a complex anisotropic material with a single material in Slope W. Through a detailed analysis of a rock cut example, we could appreciate how the joint set dip will affect the resistance on inclined planes. Resources related to this webinar are available online. The rock cut example file demonstrated in this webinar can be downloaded from the GeoStudio website at geoslope.com. An online Slope W Fundamentals course is available through the Seequent Learning portal. The only thing required to take this course is a Seequent ID, which can be created for free. And a new slope stability verification manual is available on the GeoStudio website or on MySequent. To learn more about GeoStudio, there are also many tutorial videos, example files, engineering books for each product, and past webinars available on the GeoStudio website. We have now reached the end of this webinar. I hope you have appreciated this introduction to the compound strength material model in Slope W. A recording of this webinar will be available to view online. Please take the time to complete the short survey that appears on your screen so we know what types of webinars you are interested in attending in the future. Thank you very much for joining us and have a great rest of your day. Goodbye.